Okay, so here's our steps for successive approximation. This basically builds on that small x approximation, but we can use this even when this approximation sort of fails. So first we'll make an initial guess for x, which we'll call x0. Normally that's 0, that's the small x approximation. We say x is really close to 0, but we could guess something different if we wanted. Then we plug that guess in anywhere x is added or subtracted, and solve for x1, and we just repeat this process until x stays constant. So here's what this looks like. Remember, we have our expression for k is equal to q, which is 2x squared over 0.05 minus 2x squared times 0.05 minus x. So the way this works is that here we have an initial guess. Generally, that's going to be 0, so we'll say x0 equals 0. That's our initial guess. We use that anywhere x is added or subtracted. So that's going to go in right here and right here, because here we're going to say, again, the same way we use for the small x approximation, 0.05 minus 2x is going to be about 0.05, and 0.05 minus x is going to be about 0.05. So we'll use our guess in these places, and then we'll solve for x up here, because this is just, a number. It's not, x isn't exactly 0. This will let us get a new, better guess for x. So now we'll solve this equation for x. So the way that works is we'll take and multiply both sides by this denominator stuff. When we do that, we get 2x squared is equal to 1.79 times 0.05 minus 2x naught times 0.05 minus x naught. We can take the square root to get rid of the square on the left-hand side. And then we'll divide by 2. So we have 2x is equal to square root of 1.79 times 0.05 minus 2x0 times 0.05 minus x0, and we'll divide that by 2. And that gives us our new value of x. And now the basic thing we're going to do here is we just keep solving for x until it stays constant. So let's do the first option here. So now I'm going to say x is equal to, this is x1, this is our first time through, square root of 1.79 times 0.05 squared times 0.05 over 2. And that's because my initial guess was x0 equals 0. So this gives me 0.0075 molar. So that was sort of step 2. We solve for x1 is equal to 0.0075 molar. Okay, now we're finally on to step 2. So we're going to repeat this process for x until it stays constant. So by repeat, instead of using x0 now in this equation to approximate the concentration of these large concentration species, we'll now switch this to x1. So instead of plugging in x0 equals 0, we'll plug in x1 equals 0.0075 in here in these two places. When I do that, I get this equation. So again, just substituting in instead of x0, 0.0075, which is our new value, x1. This is going to give me an x2, which when I solve it is equal to 0.0057. Now I do that exact same process, just repeat. Instead of using 0.0075, I use 0.0057. So that's what my equation looks like. Again, you don't need to write this out. I'm just doing it here for your benefit. The easiest way to do this is just to keep typing this into your calculator. So that's what I get for x3, 0.0054. This change is starting to slow down. If you calculate this out, this is just over a 5% change. So maybe one more step should get us close to the correct answer. And okay, and so if I do that one more time, again, plug in, I get 0.0055 molar. So now this is changing very little, and this is now my final value for x, since my change is now really small. We're really honing in on the correct value of x. So this is my value of x, and then I can use that to solve for any of the concentrations that I would need using my ICE table.